Hey everybody, it's Mr. Woodward. Let's talk about fundamental properties of electric circuits. So electric circuits are built upon four fundamental properties, and I've got this illustration of a stool called the stool of electric circuits, and it is being supported by four legs. Okay, so current is one of those supportive legs, power, voltage, and resistance. And we're going to use abbreviations for each of these. So for voltage, we're going to use the abbreviation of V. For resistance, we're going to use the abbreviation of R. For power, we're going to use P. And then for current, we will not use C because C is already used for other things in physics. C is the speed of light. And so we're going to use the letter I because that's available. So V, I, R, and P. Voltage, current, resistance, power. Let's start with the first one, voltage. So voltage is created when there is a difference in electric potential energy. Okay, a difference in electric potential energy. Kind of like how wind is produced when there's a difference in air pressure. Okay, no air is going to flow unless there's a difference in air pressure. So voltage is like electrical pressure, right? And it supplies a push to electrons. Electrons gain energy at the battery only to lose that energy little by little across each device that's connected to the battery. You can also think of the voltage as an energy gap between the two ends of an electrical device. Voltage is measured in the unit of volts, okay? So think of the battery as like an electron pump pushing electrons through the wires of an electrical circuit, okay? And if you think of the battery as a pump moving electrons, there's kind of a water analogy that's useful as well, right? So water doesn't flow unless there's a difference in pressure. So up here would be high pressure, and down here would be low pressure. And water always flows from high to low pressure, just like air flows from high to low pressure. Okay, so that's what a battery is providing, sort of like a difference in this electrical pressure, and therefore it can pump electrons through a wire that's connected to it. Okay, and voltage is the name for that difference. An ordinary battery that you'd buy at the store has a voltage, or meaning a potential difference of 1.5 volts. And you can see that the positive end of the battery is labeled here. That's the side with the little knob, and the negative end is the other side. And the voltage of a battery is usually printed right on the battery, in this case 1.5 volts. So over here we can say that voltage is the idea of electron push. Okay. A voltage supplies an electron push. All right, the second fundamental property is current, which confusingly we use the letter I because that is available. Current is the rate at which electrons flow through a conductor like a wire, and it results when a voltage is applied across a conductor, and a conductor would be something like a wire. It's helpful to think of current like water that's flowing through a pipe where the battery is the pump. Current is measured in the unit of amperes, where 1 ampere is 1 coulomb per second. Okay, so this is supposed to be a wire, and I mean this whole thing is a wire. And inside, you can think of each of these as electrons flowing through the wire. Okay, so they would be flowing in this direction. So the current is to the right because the electrons are moving in that direction. And the way that we would measure the current is to basically count how many coulombs of charge are passing through a wire in a given amount of time, exactly the way that you would measure the flow of traffic, right? Someone would count cars that are moving down the street, and they would say that traffic is flowing at 35 cars per minute or something. In the same way, current is being measured here in the amount of charge passing per second. So if voltage is electron push, then current is electron flow. Okay, electron flow. All right, next, resistance. Resistance is a hindrance to the flow of electrons, and every electrical device has it. There are even tiny devices called resistors that provide resistance in a circuit when you want to limit the flow of electrons. Lights, microwaves, speakers, computers all have resistance and can generically be referred to as resistors as well. Resistance is measured in the unit of ohms. So we talk about ohms of resistance, okay? So resistance is like electron friction. Just like air resistance, right? Air resistance is going to slow down the movement of an object through the air, and electrical resistance is going to slow down the movement of electrons through a wire. And going back to the water analogy, right? Less resistance here means that we have like a very wide open pipe where water can easily flow through, but here there's like a little crimp in the pipe. And in that location of the crimp here, we have resistance. Water cannot flow as easily. Now, resistance can also be used for advantages. One would be that inside of a light bulb, and here's our light bulb. Inside of a light bulb, there is actually a piece of metal, which is the resistive element, and that thing, actually, when it heats up, this is the element. When it gets hot, because of all its resistance, it produces not only heat but light and will glow. And that's how an incandescent light bulb works. There's a filament inside with a high resistance, and therefore it will glow and produce light. Okay, so that's voltage providing the push of electrons. Current is describing the flow. Resistance is this sort of friction, the resistance to flow. And then they work together like this, okay? So current traveling along a wire is like water flowing through the pipes. The more pressure there is, the more current you get, okay? So current is that flow. Voltage is like the pressure in a water tank forcing water through the pipes. And then a valve in a water pipe creates the resistance, right? Because a valve literally, when you tighten a valve, there's usually like an object here that actually moves up and down. And there might be something on the other end. And when you tighten the valve, it actually closes this gap or opens the gap, right? Which narrows the passageway through which water can flow. So the valve works as resistance. Current, voltage, and resistance. Okay, finally, what is power? So power is the rate at which energy is used by an electrical device, and it's measured in the unit of watts, okay? The rate at which energy is used. 1 watt is 1 joule per second. J is for joule per second. So a 60-watt light bulb uses 60 joules of energy every second. Power is directly related to how much a device will cost to operate because it describes how energy efficient it is. So you can think of power as electron energy. I'm going to add usage to that because it's describing the rate at which it's used. For example, these 3 lights are all giving off the same amount of light, okay? They provide equal brightness, but some are more energy efficient than others. So this one here is using 40 watts, which is 40 joules of energy every second. But this one only uses 11, a compact fluorescent, and this one only uses 7, which is the newer LED bulbs, okay? As a result, this one is going to cost $4.82 a year to run. This one will cost $1.32. This one will only cost 84 cents per year to run. Okay, so the more energy efficient the light is, the cheaper it will be to operate. However, you'll notice that these bulbs are also quite a bit more expensive, 10 to 25 bucks per bulb, as opposed to only $1 to $2 per bulb. Okay, power is the rate at which the energy is used. All right, so that's voltage, current, resistance, and power, the 4 fundamental properties of electric circuits.